Hello and welcome back. Today we're going to talk about section 2.2, which is called limits. And we're going to start with a little bit of a warm-up problem. So in the warm-up problem, what we see is a table of values. We have different x values and different corresponding y values. And you'll notice that the y value when x is 3 is missing. So I want you to, based on the table that you see, what is your best guess on what that y value should be? And if you can, think of a word that you would use to describe your reasoning. So, based on this, I would say, looking at the y values, it looks like there's maybe a pattern or a trend, so those are the words that I'm using to describe my reasoning, for why I think that y value would be 1. Right? Doesn't it seem like that y value should be 1? Up until that point, you have 0.7, 0.8, 0.9, so it looks like you're adding 0.1 each time. And then if you add 0.1 to 0.9, you would get 1. And then past that, you also see if you kept that pattern going, 0.1 increasing. So it looks like, based on the evidence, or the pattern, or the trend, that y value should be a 1 there. And that's our best guess. So what we're going to do today is talk about these type of situations where we might not exactly know what the y value is somewhere, but just based on the evidence, based on what's happening around that spot, we can make our best guess on what that y value should be. Before we dive deeper into this material, I do want to mention maybe the elephant in the room. What the heck does this have to do with what we talked about in the previous section, AROC and IROC? Well, you'll remember that IROC, the instantaneous rate of change, was the slope at one point, and those problems were a little bit tough. So what we're going to do in this section is we're going to talk about a concept that is very much related to IROC. It's going to help us do or solve some of those problems that are a little bit tougher, and I'll try to point out those instances when we come across them. All right, but let's get into it. 2.2, and it is limits. So we have some good definitions here. You'll want to write them down as well as some new notation that's very important that you'll want to write down. So what is a limit? Well, the limit of a function, f of x, is the y value that the function approaches as the x value approaches a certain number. So you might have to read that to yourself a couple times to understand it. But thinking about the warm-up problem, the y value that a function approaches when x approaches a certain number. So basically in this last problem, we would say the limit would be 1 when x approaches 3. We didn't really know what the y value was, but it's what the y value seemed to be approaching. Looking based on the evidence around, it looked like the y value was going to be 1 when the x was 3. So we call that a limit. And we also use special notation. So this is the notation we would use for the example up above. We would say the limit of f of x as x approaches 3 is 1. So you'll notice I'm pointing at the paper here. This is how we write it. The limit, so we write lim with an f of x next to it. So the limit of f of x as x approaches 3. So below the lim, we write x with a little arrow pointing towards 3. And that limit has a value of 1, so that's why I'm writing it equals 1. So we want to get comfortable with this notation, as well as the definition of what a limit is. Before we look at some more problems, we're going to look here at the informal definition of a limit. So it's basically what we just wrote before, but without specific numbers. So we say the limit of a function f as x approaches a is L when the y value of f gets closer and closer to L as x gets closer and closer to a. So of course here a and L are numbers. We just don't know what those numbers are because this is a generic definition. But the limit of a function is going to be a certain y value if it looks like the y values of the function are approaching that particular value when the x values are approaching a certain a value. All right, so that's good to know. We will talk about the formal definition, so you might be wondering, this is called the informal definition. What's the formal one? The formal one is definitely more mathy. It's actually 2.3. It has its own section. I'm going to mention it at the end of this section, but we're not going to talk too much about the formal definition of a limit. Okay, before we get into our next example, I do want to mention How can we use this in real life? So limits might sound like something you haven't heard of or used before, but I mean, if you think about it, patterns, trends, using evidence is important in a lot of aspects of life and a lot of career fields, medical field, meteorology, business, politics, law. So lots of different times where we use evidence to predict things that are going to happen that we don't necessarily know are exactly true. Okay, so finally, yes, our next example, we have another table of values. We're actually given a specific function this time, but it doesn't really matter too much. We have a function, f of x equals x squared minus 1 over x minus 1. And we're given a table of values, particularly where x is 1, so that's kind of our focus. We were not given the y value there, so you can see that it's missing, but we were given x values very close to 1, and also the y values corresponding to those x values. So I do want to mention, if you were to plug 0.9 into this function, f of x equals x squared minus 1 over x minus 1, you should get a y value of 1.9. That's what this table means. So they're giving you x values and telling you what the y value would be if you were to plug it into the function. So they gave us a bunch of them. We're missing the y value when x equals 1. And we're asked here to find the limit of f of x as x approaches 1. So that's asking us, well, what do you think the y value is going to be when x is 1, based on the evidence around it? And I would argue that you would pretty clearly see that it should be 2, right? Because everything up until that point is getting so close to 2. You have 1.9, 1.99, 1.9999999, and then just after that you get 2.0001. So it looks like that y value should be 2. That's our best guess, and that's going to be our answer. Based on the evidence, the y value should be 2. And that's that. So I know you might have thought that was a trick question, but it wasn't. That's what it is. But what makes this example special is maybe why you could have thought it was a trick question, because if you actually do try to plug 1 in to this function, what do you get? You end up getting 0 over 0, which is undefined. So technically, f of 1 is undefined. So when you plug 1 into the function, you do get an error on your calculator if you did it on your calculator. It's undefined, but that doesn't matter because the limit is not asking me what is the y value. It's asking me what does it look like it should be. So that's the difference between a limit and an exact value. The exact value of this function is undefined, but based on the evidence, it should be 2. So the limit is 2. So I emphasize that with these special notes here. You might want to write them down. This example is special because the value actually doesn't exist. It's undefined there, which tells us that a function does not need to be defined at a point in order for the limit to exist there. It doesn't actually have to have a y value in order for it to have a limit. So make sure you write that down. It's going to happen quite a bit for us. All right, next up. So another example, we have a function, another table of values, which is very helpful. So what are we going to do here? Here we have a function g of x equals 1 over x. In particular, we're given the values where x is 0, or around where x is 0. We actually were not given the value when x was 0. And we're asked to find this limit. So you want to be able to read this limit. This is the limit of 1 over x. That's the function that we were given. The limit of 1 over x as x approaches 0. So this is asking us, what does it look like the y value would be based on what we see, based on any kind of pattern or trend that we see? So take a look, think about it yourself. Is there a trend or pattern that we see for the y value here? And you might find the answer to that to be a little tricky, and I wouldn't disagree with you. There is definitely like a pattern. The problem is that our pattern doesn't really seem to agree. So it looks like if I'm looking really on the left side of 0, so where negative numbers are, the y values seem to be negative, but also getting bigger. So we have negative 10, negative 100, negative 1,000. So the next one I would guess would maybe be negative 10,000. based on just that trend. However, on the other side of 0, those numbers, while they have a similar pattern, you'll notice that they're positive and not negative. So based on this pattern, it looks like 10, 100, 1000, I should have a y value of positive 10,000. Isn't that what you'd think would be next? So on the left side of 0, where we have negative numbers, it looks like we should have a y value of negative 10,000, but on the other side it looks like we should have a y value of positive 10,000. So that's an issue. I don't really see a clear pattern or trend. They're kind of disagreeing. The information that we have does not agree on one y value, and that's an issue. When our y values don't agree, our pattern does not result in one final answer, then we say the limit does not exist. And we often write DNE, does not exist. So in this case, we would say this limit does not exist. And it's really because the y values don't agree as we approach 0 from both sides. The pattern disagrees. One pattern is going to negative 10,000, the other one's going to positive 10,000. They're going two different places. So make sure you write this down. It showed up here in kind of an orangey brown color. DNE does not exist, and the reason is because the y values don't agree on a single number. So you might remember this. This is one of my favorite movies, Mean Girls. So there's a very popular scene in that movie where she says, if the limit never approaches anything, then the limit does not exist. So that's what's happening here. These y values are not approaching anything specifically. There's no clear pattern, so this limit does not exist. All right, so what we're going to do next, that was us looking at tables of values. It was a little bit easier to see if there was a pattern here. Next up, we're going to look at graphs. So what if we just have a graph? How do we find limits looking at a graph? And then finally, at the end, we're going to look at limits algebraically. That means, what if we just have x's and numbers? How do we find limits there without a picture, without a table? And that one's a little bit tougher, so that's why we're doing it last. So next up are graphs. What I have is a little handout that I'm going to be going over. So I've printed it out. I put it online for you to print out too if you want to. If not, you can just follow along with the slideshow, but it's definitely going to be easier when you have this because we're going to talk about a lot of graphs, so you don't want to draw them yourself. You can print this out. Okay. So a couple reminders before we start doing this, just to recap a few things that we learned. A function does not have to be defined at a point for the limit to exist there. It's going to be very important. But the function does need to agree on one y value from both sides, from the left and the right. That's what we were talking about before in that last example. We have to agree. Our y value has to agree on one y value from both directions in order for the limit to exist. So we're going to look at graphs, keeping these things in mind. And the test that we're going to use for limits on a graph is called the two-finger test. So I'll tell you what that is in just a second. So what we're going to do is focus on this handout. We have one graph drawn here with a lot of kind of crazy stuff going on, and those are going to affect our limits. But one thing that I like about this sheet is it emphasizes the difference between two things. So limits, which is our new concept for the day, is asking us what does it look like the y value would be or should be based on the evidence, which is different from what is the exact y value. So it's almost like what should it be based on what's happening nearby, not like what is it when I look at it. So we're going to emphasize the difference between those two things in these problems here. So here's a graph, a lot going on. The first problem asks us f of 0. So f of 0 is what is the exact y value when x equals 0. So they give us an x value of 0. What is the exact y value? So I can look at this graph. When x is 0, I go up to the graph. It looks like it has a y value of 1. So the exact y value of that graph when x is 0 is 1. There it is. It's a point. It's filled in. It's clear. It's obvious. It's 1. Part B is a little bit different. Part B asks us what's the limit of f of x as x approaches 0. So this asks us, what does it look like, or what should the y value be when x approaches 0 or x equals 0 based on what's happening around that area. So this is when we use the two-finger test that I mentioned a little bit earlier. So for limits, what we want to do is we want to find, of course, where our focus is. So our focus is at 0 when x is approaching 0. So x equals 0 is there. What we want to do is we want to put our finger on the graph to the right and to the left of that area. Make sure it stays on the graph. By the way, when I say the graph, I mean the bolded actual curve. A lot of people think graph means like the grid, but that's not the graph. The graph is what's actually being plotted on the grid. So you want to put your fingers on the graph or the curve. Make sure one of your finger is to the right of your focus area, one finger is to the left. So what you want to do is you want to move towards 0, so where x is 0, so you want to move towards that, move both of your fingers, but keep your fingers on the curve. So as I move my fingers closer to 0, you'll notice that they are meeting up, right? They're going to touch. Ooh, they touch, they run into each other. And that's a good thing. That's checking for if they agree or not, because that was an issue we had in a previous problem. The y values didn't agree. Here, because my fingers meet up on both sides, that means they're agreeing on a y value. And let's see, what is that y value? Well, that y value is 1, right? That's the y value where x is 0. I know it might seem weird at first. This is our first example. But trust me, the two-finger test will help a lot, especially as we move forward with more examples. So based on the two-finger test, it looks like the y value should be 1. My fingers met up, and they met up at the y value of 1. Okay, so let's try another one. F of -5. This is not a limit. This is what is the exact y value when x equals -5. So x equals -5 is right here. There's an asymptote there. We know that if there's an asymptote that the graph does not exist. So the value is undefined. That's what the y value of the graph is. It's undefined. Please don't put does not exist. We only use that for limits. I know I said does not exist, but it's more like the point didn't exist, so the y value is undefined. There is no point, so the y value is undefined there. Let's talk about the limit. So the limit, I'm going to use the two-finger test again. My area of focus is at -5, so I want to put a finger to the right of that. So I'm putting a finger on my graph that's to the right of -5, and then I'm going to put a finger on the graph that's to the left of -5. And I want to keep my fingers on the graph but move towards -5. So I'm moving towards -5. My fingers must stay on the graph, so you'll notice that they're kind of separating from each other now. So I'm keeping on the graph, moving towards -5. And what am I noticing? Are my fingers meeting up? No, they're not. Do you see? My fingers aren't touching at all. So that's a problem. In order for a limit to exist, my fingers have to agree. My y values have to agree on both sides, and these y values are not agreeing. They're actually going in complete opposite directions. So therefore, this limit does not exist because the y values do not agree on the left side and on the right side of my x value. So this is a D and E, does not exist. The y values don't agree based on my two-finger test. All right, let's keep going. So f of 7, that's next. F of 7 is the exact y value when x is 7. So let me find where x is 7. That's right here. What's the y value there? You'll notice that on the graph, there's a hole in the graph. So there is no y value. So this is undefined. Because of the hole in the graph, it's not filled in. There is no y value. So the y value is undefined when x is 7. But that doesn't necessarily mean that the limit does not exist. So let's talk about the limit. So the limit is going to be what should the y value be based on the evidence when x is 7. So I'm going to use the two-finger test. I'm going to put my fingers on the right side and on the left side of the graph around that point. And then I'm going to move my fingers towards x equals 7, but keep my fingers on the graph. So you'll notice that my fingers do meet up, right? They do agree. They're meeting up right here. So my fingers meet up, so they're agreeing on a y value. And what would that y value be? It would be the y value here at -5. That's the y value of what that point would be if it was filled in. So that's going to be the limit. The limit does exist, and it is -5. Now I know what you're saying, whoa, 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 whoa. I thought there was a hole there. There's not a y value there. And that's true, the graph is undefined there, but the limit doesn't care. The limit is looking at a pattern. It's looking at a trend. Based on this graph, what's happening around this hole, where does it look like it should have a y value? It should really be a y value of -5 there. Like, that's a random hole in the graph, right? You wouldn't anticipate that to be there. So a limit's like, well, if all things work out, like, where should the y value be? And the y value should be at -5 if things worked out nicely. So that's what it's saying. All right, we have one more example together. F of 4. So 4 is here. F of 4 is what is the exact y value of the graph. So we actually have sort of a jump in the graph, or a gap. But we do have a point that's filled in when x is 4, and that's a y value of -2. So the graph is defined. It does have a filled in point when x is 4, and its y value is -2. So f of 4 is -2. Let's talk about the limit. So the limit says, based on the trend, is there an agreed upon y value? So I'm going to put my fingers on the graph to the right and to the left of 4. So this is where I want to end up when x is 4, but I'm putting a finger out to the right and to the left. I need to keep my fingers on the graph as I move towards 4 on both sides. And what happens when I actually get to 4? Do my fingers meet up? No, they don't. My fingers do not meet up when I get to 4. So therefore, the limit does not exist. These do not agree on a y value, not on a single y value. They have to agree on one y value. They do not do that. So therefore, the limit does not exist. There is not one clear trend or pattern. The left side of the graph is going to a very different y value than the right side of the graph was going to. So that's why the limit doesn't exist. They just don't agree on one y value. So I really like this example because we saw a bunch of different situations. We saw maybe in the first two where the situations kind of matched and made sense a little bit more. And then in these last two, we saw where they kind of flip-flopped, where the function's undefined, but the limit did exist. And then the other one where the function was defined, but the limit did not exist. So if any of these were unclear, please rewind and rewatch this. What I'd like you to do is work on these few examples yourself, just to get some practice. So here are the first three. If you've printed it out, you can see all of them yourself, but if you did not, you'll want to copy these down. So the first three, and then these last three, they're all asking you about the limit as x approaches 1. So pause, try them yourself. I'm going to go over them very quickly right now. So the first example, the limit as x approaches 1, here we have a graph. Here is where x is 1. So if I put my two fingers on the right and on the left and head towards 1, they're both going to meet up and agree. What is the y value where they meet up? They meet up at a y value of -2. So that's going to be the limit's value there. Part B. So we're again approaching 1. We have an asymptote there. So this is very similar to what we saw for part D up above. We put a finger on the right, a finger on the left. We head towards 1, but we have to keep our fingers on the graph. So our fingers are heading in opposite directions. They do not meet up. They don't agree. They don't touch. So therefore, this limit does not exist. That graph does not agree on a y value when x is 1. Okay, part C. So here we have, looks like an upside down parabola. There is a hole in the graph, but holes don't really matter for limits. So I'm putting a finger on the right, a finger on the left. I keep my fingers on the graph as I head towards that point. My fingers do meet up, they touch, and the y value where they touch is 3. That's what the value should be. Based on the trend, there is nothing indicating that there should be a hole in the graph there. So based on what's happening around that point, it looks like there should be a point at 1, 3, a y value of 3. So that's what the limit is. It's a pattern. What does it look like the point should be? It should be 3. That's what the y value should be there, based on all the evidence around that point. All right. So next up, we have this graph here, another kind of jump or gap situation. So we put a finger on the left, a finger on the right. We head towards 1, but we have to keep our fingers on the graph. So our fingers do not meet up. They don't agree on a single y value, so therefore this limit does not exist. All right, this one's probably one of the trickier ones. We have another asymptote situation. So you might have thought, well, maybe all asymptotes are D and E, but that's actually not the case in this problem. So here we have the limit as x is approaching 1. So we're going towards 1, towards that asymptote. We got to put our fingers on the right and on the left, and we keep our fingers on the graph as we approach x is 1. So you'll notice that our fingers go up and up and up forever, but they do essentially touch. I realize these graphs will never touch each other. They'll never intersect each other, but our fingers basically do, right? Our fingers get so close that they're agreeing on a y value. But you might say, what is that y value? Like, I don't see a point. But what would you think that y value might be as you go up and up and up forever? That y value is infinity. So this graph agrees that it should be going up to infinity. That y value would be all the way up to infinity up there. And it agrees on the left and on the right that that's where it should be going. So that's what we say. The limit of e of x as x approaches 1 is infinity. All right, the last one, very similar to the first example here. It's actually the same graph, but there's just holes in this graph. But we notice that holes don't really make a difference in terms of limits. So as we approach 1, let's put our fingers on both sides. We approach an x value of 1. Our fingers do meet up. They meet up right here at this point where there's a hole in the graph. And that hole would have a y value of -2. So that is the limit's value. All right, so this takes lots and lots and lots and lots and lots of practice. Please make sure you're doing that and asking any questions to clear up any misconceptions. What I'm going to do is I'm going to take a break now, and then I'm going to come back and we're going to talk about limits algebraically. That means if we don't have any pictures to look at, if we don't have any tables of values, we just have x's and numbers, how do we find our limits then? So stay tuned. I'll see you in a little bit.